Hello everyone, and welcome to the 14th and last tutorial of the Functional Data Structures course. Today I will cover material that is not really relevant to the exam, but it's more about using Isabelle to do refinement of implementations and to generate code. Okay. So the example problem that I'm going to work on is basically we basically want to generate an standard ML program that given a list of words gives you an assorted list of pairs, the first member of which is the word, and the second member of which is the frequency of that word in the initially given list. So let me show an example here. So for instance, actually the examples are just in the sheet there. So for instance, if we're given A, B, B, C, C, then we want a list C frequency 2, B frequency 2, A frequency 1, and it's sorted according to the frequency, okay? So let me just go quickly with you over these definitions before we implement anything. So now we have what we're doing is just specifying abstractly properties of the function that we want to implement. So here, for instance, let me just so here we're specifying that if we're specifying basically what it is to be what is the natural what is the natural number that is a frequency of a given word. Okay, so you're given a list of words and a word, and you want to return the number of times basically that this word occurs in the given list. Okay, so the way this is defined is, okay, we transform the list into a multi-set. So it's a set that has it's basically a set that can contain repetitions of the same number. And count is just a function that is generated by the data type package when we're defining the multi-set type here, and that function basically for data types that you define, like for example, if you define an alpha tree, then count of that count that is generated for this alpha tree will just be the number of alphas in that tree, so the number of data elements. Okay, so based on these two functions, we have frac ws. Okay, so this is a function. So basically, you give it a list, and it returns to you a function that if you give it a data element of the type that exists in the list, it will give you the number of occurrences this element occurs in the list. Okay. So let me just quickly do an example here. Okay, so I'll just write it quickly, it's easier. So for instance, if we're given a list A and B, okay, so the multi-set of that is just this, okay, and if we want the count of that is going to again be a function, but this function takes a character list and returns to you an at. Okay, so for instance, if I want to count the number of A's, I just give this function that came out of that thing A, and then it gives you how many times the A occurs in the multi-set equivalent to this list. If we just add another A, okay, then it has 2, which is 3, then it's 1, okay? So that's what it means to be a frequency. So now we want to, the first thing, we want to define what it is to be a frequency list for a given list of pairs of that type, okay? So as I said, I want to get a list. I want to get a list for a given list of words or say lists of characters. I want to get another list of words, another list of pairs and each of those pairs contains a word and its frequency, if the word exists in the list. Otherwise, it shouldn't be empty, or it shouldn't contain the word basically. So here, so how can we define is frequency list such that, for example, this is a list, this is a frequency list, okay? So you should probably pause this and try to do it yourself. Okay, so the way I will do that is basically I will firstly start with a predicate that is true for any given list and list of pairs, and then I will change it to basically fit these test cases that are given in the sheet, okay? And so it's frequency list, so words, for instance, and frequency list, okay, it should be true always, okay? So given a list of words and then frequency list, this is always true, okay? So that, well, firstly, we would know that we want the list to be sorted with respect to the frequencies. So we want the bigger frequencies to occur earlier, okay? So that's one thing. So map the second frequency list is the list of frequencies. We want that to be sorted. I think it should be. Let's see what sorted is. Is it ascending or descending? It's ascending. We want it descending from the bigger to the smaller, okay? So the reverse of this list should be sorted, okay? Okay, and what else do we want? We don't want the same occurrence to happen for the same word, and that's why this test fails, okay? So distinct map first frequency list, okay? So the words are distinct, and of course we want the numbers to actually be the frequencies, so we can just do that as follows. So for all pairs such that one of them is a word and another is a frequency, and just make sure. So in the frequency list, we want what? We want the frequency to be equal to count the number of times W occurs in the list W's, I think. Okay, so here I made a mistake. Oh, that should be frequency. Okay, so now all of the all of the test cases hold, okay? Okay, so now that we have specified what is a valid frequency list, now let's try to implement a functional program that computes the frequency list given a dictionary, or like a list of words basically. So compute. So here the first implementation, we want to do something like what I will show you now. So remember, if you remember that there was this notation that says the following: given a function, in Isabelle HOL, a function f, okay, we can change what, so given a function f firstly that maps alphas to betas, for example, we can change the value that f maps a value a to by the following notation. So f would, I want to change the way it maps a to b, for example, okay, and it used to map it to c, okay. So that was one way of changing a function, basically, or modifying a function, okay. So the way, now I'm going to implement a function that computes this frequency list just by utilizing this notation that I just told you, okay. So this should be a fold. So first let's do this one. So this is a function that, given a word and a frequency mapping, it basically causes this frequency mapping to map that word to one more, okay, and then the reason we're going to use this function will be clear. The reason I'm defining this function, you know what, I will just write first on paper what I want to do. So firstly, I want to do like a fold, okay, of this function increment one on the given list of words, starting with a function that maps everything to 0, okay. So if we apply that function to, for example, just if let's say like we have a, b, and c. So let's say this is w's, and then let's just apply that, okay. So this function should be such that increment of, for instance, here it's like a function that takes anything and maps it to 0, increment 1 and a. This should change that function into a function that maps a function that maps a to 1, okay. And the way we would write that, we would change this function to be the same as it was, but just have this change in it, is by writing lambda and then equals 1, okay. And then this is the first step of the fold, and then the fold function will then take this, okay, and apply again increment 1 to it with b. So this we have to then change this function by changing the mapping of b to also 1, okay. Now this is the second step of the fold. Now the third step, which is the c, is going to take this function and change it and make it map c into 1, okay, etc. Okay. So okay, and then we can keep going like that. But the general pattern here is not that you actually take the word that you found and map it to 1. No, you map it to what the original function mapped it to plus 1. Okay. So the way we specify a function increment that does what I just showed you here is as follows. So increment of x and then f equals f of x. So that was the notation of updating a function. Whatever f mapped x to plus 1. Okay, so that is increment, and then frequency 1 should be that way. So this is the first implementation of the function that gives you a frequency list. Okay, so for instance, if we apply it to that, let's see what if we apply to that. So here we got the function, okay, and let's apply A. Okay, so it gives you 1, for instance, for A, and 2 for B, and 2 for C, for instance, etc. Okay, so now that is that basically is the first refinement of our abstract specification. Okay, so specification here just says what is a frequency list, and this is the first executable implementation to compute this frequency list. Okay. Sorry. This is the specification of what a frequency list is, and this is our first characterization of a way to compute these frequencies, but that's not necessarily executable. Okay. So the first refinement is to make this executable with this fold implementation. Okay, so now we know how this executes. Actually, also count is executable, but I don't know how it is implemented, and it's, as I said, implemented by the data type package. So the point here is that you can have this specification of a function that is not even executable or probably inefficient, and then you've refined it into something that is executable and maybe efficient. Okay, and then you show that what you refined, that your refined version is the same as the original version. So let's do that. Equals frequency w's. So when you're putting two functions equal, usually it's good to show the first step that they will be equal for an arbitrary thing, for an arbitrary argument. So here, for any argument, w for instance. Okay, and then here I will just see induction on the word w's and see if it works. Yeah, it doesn't work. So frequency 1 we need to rewrite with the definition of frequency 1, I think. Okay, and frequency. Okay, so what do we have there? So we have here the induction hypothesis. It assumes that we have a function of upside equal to 0, and the problem is that this is this is a different function. So we actually we actually need to have a more general lemma that talks that generalizes the function, I think. So how can we do that? So let's, I think we need a separate lemma like that, or what? Oh, no, we don't need, let's first unfold the definition of increment one and see what happens. Okay, so now we have that, and that, Okay, so we need to prove this as a separate lemma. Folding So we need a separate lemma. Well, we need to generalize the function, that's for sure. Okay, how can we generalize this into a good lemma? So let's try and do that. Okay, so this should be a general function. That should be plus f of w, okay? Because here what we're doing in this fold, we're increasing the number of w's. We're increasing whatever f maps w to as we're going over the list. So we can just basically count the number of w's in the list and then increment them, okay? And then we will do the same thing. Induction again on the words and arbitrary the function this time. Okay, we still yeah, that does it. Actually, I'll just put it inside the proof. Okay, and then we should be able to show thesis by just unfolding the definition of the frequencies. Like that, yeah. Okay. So that is the first thing. What we did here is that this implementation implements that more abstract version of the function that we don't really know how it is implemented and sometimes be executable. Okay. Next, the next implementation, we want to make our implementation even more efficient, and then so basically we want to so let me just quickly describe what the inefficiency of this implementation is. So as you can see here, you are the way your like the way this function would actually be implemented is like a list. As you can see here, you're just adding more and more entries to it, and then when you're looking up a value, you will just keep going, seeing all the map lists that you added to the function, the mappings that you added to the function, until you find one that the first one that matches your the value that you're searching for. So we want a more efficient version of that, and a very effective way of implementing maps is by balanced binary trees. And here I'll just do the red dot tree implementation. Okay. Here what we want to do is implement the map as a red back tree, as a balanced tree, which will be much more efficient when you're accessing it, in order for you to do these incrementations. So this is so those two functions. So this is an abstraction function of that basically shows like should show you the equivalence between the red black tree and sorry, that should basically treat the red black tree as if it is the other function that we did up there, which was more abstract, like this frequency one, that frequency one. Okay, so here, given the red black tree and an element, what is the frequency of that element? Okay, and that should, if we want that, well, that should be like this. Okay, so you either look up. You remember we had these operators on the map implementation with red black trees. Look up. So that given a key, given a tree and a key k, you look up. It returns none if k is not in the tree. If k is not a key in the tree, otherwise it returns some value v. Okay, and this way we will get either a 0 if something that was never seen, or a value v if a word was seen before. Okay, so let's copy that. Okay, I'll just copy them from somewhere else, or I'll copy them and edit them myself. Okay, so now we have the first one, and the second function is that is an invariant that we need to make sure it applies to the tree all the time, and that invariant is basically it doesn't have any entry that is a 0. And the reason for that, well, firstly, remember that frequency lists should not contain entries whose frequency are zeros. Okay, so if we want to implement this with red black, if we want to implement a function that computes these frequencies with red black trees, it would be easier for us to just rule out all of those elements whose frequency is 0, and then the frequency list will just be of another folding of another increment function that, instead of incrementing what we like that, will increment. We will just be almost the same one, but that just uses the RBT insert operation. Okay, like to update the map. Okay, so first of all, let's just make sure that the first like in the beginning, an empty red black tree is basically an empty red black tree is exactly like this function, which maps everything to 0, which is what we used initially for here for our other implementation. And the second one is that the invariant holds for RBT empty. Okay, so FM. Okay, it's the emptiness. Now let's define another function, increment, that should be used in the same way as the folding, but for red black trees. Okay, so it will be very similar. Okay, so let's take the original one and just replace whatever is in it with the red black tree equivalent notations. Okay, so what we will do is basically update, or like red black tree update that given tree with, so firstly let's see the what does update expect? The tree first and the key first. What is it called then? Oh yeah, it's insert, sorry. Okay, so it takes this one, so the key, the value, and then the tree. Okay, so here the key will be x, the value will be tabs finite map of the given tree and k x, but plus 1. Sorry, this should be update, should be insert. And the tree is our tree. Okay, so that does exactly what increment 1 we used to do. Okay, so now let us prove that this function increment 2 preserves the invariance, and that is equivalent to increment 1. Again, these lemmas will be useful for proving the main theorems, which is that frequency 2, frequency 2, which is increment 2, is exactly the same as frequency 1, and that the invariant applies to it. So this theorem basically shows that frequency 2 is a further refinement of frequency 1. Okay, so let me just do that. Okay. This should be underscore. No, actually. No. Okay. So let's prove that. So let's prove the first lemma. Here we can prove it by induction on the tree. Yeah, let's comment that. And then apply auto. My guess is that we will need to generalize that key. Do we need to I'm just unfolding the definitions there, and then split option splits. Okay. So if we insert successor of 1, successor of 0, okay, let's just sledgehammer down and see if that holds even. Actually, I don't know why am I doing induction. Let me just try to unfold all the definitions. And increment 1. Yeah, just that. Yeah, I'm just used to doing inductions to the extent that I'm doing them completely automatically. So what do we need to unfold there? Okay, let's see. How will we help here? We should have a lemma. Okay, so here basically what we have, we know that 0 is not in this range, and we should then know that so okay, so range, I think it's the range of a finite map. Okay, the range of a finite map. Okay, so RBT lookup transforms a tree into a finite map because it's a function that expects a key and then returns you a value. And so basically, abstractly speaking, here we're saying that 0 is not in the range of this map, and then we add a suck, like another value that is suck to that map, and then suddenly 0 is supposed to be in the range. Of course, that should be a contradiction, so I will just prove this as a separate lemma. Times 0. Okay, let me just see one last time. Okay, so firstly, I just want to see what is lookup. So there must be a lemma. Yeah. Okay. So basically, we want a lemma that transforms lookup, like that. Lookup after an yeah, okay, so this is it, but let's just do it in a cleaner way. So 0 lemma, if 0 is not in the range of some finite map, then 0 is also not in the range of that fm with the entry of some x updated to successor of some y. Okay, so here just yeah, so the range of m, yeah. Yeah. You can just do that there as well. Yeah. Okay, so now we have this lemma. And then I'll approve the okay, so now the new version of that frequency function, it's called freq2, and that one is more efficient because it uses red trees. So when it's updating, it looks up the values and the keys in red trees, which is much more efficient. Okay. So let's try and improve that. So space FM, underscore FM. So I think that sledgehammer would be doing it because we already have a lemma about okay, so we have abstract FM and increment 2, and this is frequency 2, so we need to unfold that definition. Let's just focus on the first one. Okay, so we need to unfold that definition of frec 2. Okay, what do we have now? Where's frec 2? And frec 1. So this should follow from... Okay, we know that increment 2 is equal to increment 1. And that's in the simp set. And we also know that the NT is the same as that. So here we either, I think we need to do an induction on the given list. Let's see what happens. Okay, so now let's hammer that while we're thinking. So basically we want, like we know that because the invariant holds for this empty tree, then that means that increment okay, so we need a separate lemma again, aside like what we did up there. So we basically want this as a separate lemma, as general as possible, so that we're not going to be modifying it. So this should just so this should just be an F. This should be a T, or no, it's empty and an empty. So we want to basically generalize this and generalize that by saying that so we need to get this outside. What was the lemma? So we want to use this lemma to get this outside, and we also want to have another one that gets this one outside as well. Okay, so let's do that. This is a tree plus, so on the T empty plus what was it called? ADS-FM of t for any given any word. That's it. So now we can just generalize over t. Okay, it didn't work. Okay, I'll just generalize over t. Okay. Let's see. Holes. I think we will need the invariant to hold for t. This one. Let's see. It doesn't work. Just look into that. Okay, I'll remove that arbitrary for a moment just to get things to work. Okay, so now, okay, the reason I added this invariant is to be able to get okay, let's go back to the original lemma. Okay, so here, if I just say, so if we do this as a t, and that is the abstract finite map of t. Okay, so we want to unfold this. Okay, so what we have here is okay, so we need firstly, we need an arbitrary t because this cannot be used like that, okay? Secondly, yeah, we need, basically, in order for this to fire, okay, we need this to fire in order for us to have that this equals that right? Yeah, we want this lemma. Okay, so if this lemma fires, then we have this will be written in increment 1. Okay, and then we have the other part increment 2 after folding and increment 1 after folding, and that will be done with the induction hypothesis, because we would generalize our t. But in order for that to fire, we need t to have the invariant. Okay. Let's see like that. Yeah. Okay, that does it. Okay, and so that should give us that first half. And second half, so what is frac 2? Frac 2 is that. So we want to basically show that that the invariant also should hold for that after folding. Okay. Oh, sorry, the invariant. Yeah. Okay, and now we can use that lemma to have this one proven. This. Okay, and then I'll just show the thesis. Yeah. Okay, I'll just call this goal 1, because thesis cannot have two goals. This is goal 1. And this is goal 2, and then okay, and then yeah, that just is like that. Okay, so now we know that frequency 2 is an abstraction of frequency 1, and the invariant holds for it. The last thing is get the list from the black tree by simply implementing a function that sorts a red black tree based on the keys. Oh, sorry, on the values, not the keys. Right, we need to sort based on the second thing. Okay. So let me just do that. This is right. So this function should so reverse the build the black tree. So that should be done by frequency F2. This is the list of words. And then we want to sort. So let's just see. There must be a function for sorting the black trees. Let's see that. Sort and okay. Sort key. So what do I do? So okay, so we need to sort the keys based on the values. Yep. So key does that. So sort key. Okay, so we need to do like sort key, and that function takes like a mapping from keys to values and a list of keys, and then returns to you the list of keys what is being sorted. And here the mapping from list to values would just be second. So this then is oh yeah, we need more traversal as well here. This is pretty big. Okay, so extra variable. Okay, so let's see the functions are there for the battery. So we'll just look for in order. Okay, I'll just look for functions that take a red black tree. Enter lists. What's the type called? Okay. And returns article list. Okay, and it should be yeah, so there is this function called entries. That does the in-order traversal of what we want, basically. So entries here. Okay, so now this should be it. And now what we want to show is that this thing returns returns an is frequency list. So we need to prove there are 3 components. In conjunct of that is frequency list definition. So sorted, the first one. So let's see what the hint here says. Something it says here first. The lemma of the form. Yeah. Okay. So if that looks okay, so let's just put this lemma in the hint so that I made a mistake already. So I'll just try this one of these examples. Okay. I don't know why they're using the linear orders. Oh yeah, because these are the keys and the factories wouldn't work without that. So we need the fact that there's an order on characters comes from this. Instantiation of character is in the order. I don't know why is that not working here. Is there this is just like characters or okay. Character lists. So let's just see the counter example there first. List all of those things. So 1, 2, 3. Okay. So the counter example just give an arbitrary list. Okay, what's wrong here? Okay, so here we have the opposite of what we want. The things that are less frequent are in the beginning, so we should just get the reverse of this because this whole thing is assembly. Okay. So there are no counter examples now. Okay. At least there is an obvious one. So now let's finish this. Let's go into the proof. Okay. So at least we know that if we have an entry there when we're looking up, then so okay, so frequency 1 correct. It says this is frequency 1 correct, I think. So using that, we can show, and here we have that frequency 2 is correct as well. Okay, so this would say frequency values of W equals F. Okay. Getting variance. Yeah, okay, so this is, because we cannot, like, this tree will not have anything that is 0 in it. That's, remember, we have to prove that. So we have to say here that is greater than 0. Let's see. Okay. So that should follow from unfolding the two lemmas, correct this one and the other one. And just find the total. And just add the first one also to the thing. Okay, let's see what that is again. I'll just try and do it by induction first and then see. I need to understand what is the book up, since it's a definition of what. Let's just see that. And there's some lemma here about it says if you look up in. Okay. No. So this frequency one, okay, we need to prove that if this returns some f, then what I just took there equals that f. That's not happening either. Okay, so okay, I'll just actually just discover this is red also, so I'll remove this thing from the theme set. So I'll just add it. Okay, so everything works now. And just return that lemma by pause, because I think that's this. So let me just think about why should that hold, why is the channel working. Okay, so we firstly, okay, it's not very fruitful. So firstly, we have here we should have that this is equivalent to having to having frac 2 w's and of w equal f frac 1. Let's just go slowly. So this should hold from that now, right? Okay, it doesn't. Okay, what does this then say? Abstract FM. Yeah, okay, so we need even before that to say that this is equal to abstract FM of frequency. See if that holds. That's it, I think. Okay. So here we should just simplify the definition of abstract FM definition. Okay, so now we I'll just try it like this and then see if the whole thing holds, and then you can clean up if there's time. So this is gold here. So if we're looking up something, then f is greater than 0. Okay, we have that somewhere. Isn't this the invariant? Yeah. So we need that invariant. We need to show that this we have that this invariant already holds for for this. Okay, so okay, and then there's one thing called that invariant. So now we have the lemma. Let's genre again. And then the second one. Okay. Let's try again. You know what? I will just use this like that, because it seems like it's used here for the first one as well. It's used. And okay, okay, this is happening, I think, because this is in the same set. I'll remove that now. Okay, so this should so I'm just wondering what is okay, remember this lemma that we proved about range somewhere up here? Okay, whatever, I will just leave that for now. Okay, now we have the first step. Okay, so from here, to abstract fm, and then now the rest should follow from frequency 1 correct, and frequency 2 correct. Yeah. Okay, see, okay, it doesn't. Okay, so we have that this is equal to that, and that is equal to frequency 1, and frequency 1 is equal to frequency. Okay, so what's wrong? Okay, let's see the genre returns something. Yep. Okay. No. Okay. So that's the lemma, I think, that was alluded to in this hint. Yeah, unfortunately, I wrote this a long while ago, so I don't remember exactly now why. but I probably put it there for a reason. Okay, now let's prove what it means to be this. Okay, so I'm going to do each of those as separate lemma. So we want to show that what is sorted. This is sorted, yeah. Okay, so that should follow, I think, from the fact that this works, and like, let's just see, because there must be something in the sim set about the fact that sort key is sorted. I'll just look up with sledgehammer. Yeah. Okay. Just pull that one. And the second one is that everything is distinct. That might be slightly trickier. So the keys are distinct. So how can we show that? We have a lemma that says anything about that? Ah, distinct entries. Okay, the entries are distinct. Because basically this function of sort uses entries, and then you want to say that, okay, so this is distinct. The result of that is distinct, and then this also, if something is distinct, then the output of sorting will be distinct, and the output of reverse will be distinct still. And the last thing is this. So everything in the frequency, I think this should follow. Okay, I'll just remove that because that's useless. This should follow from that lemma. So let me just so anything in that. So here so I'll just call this sum if and only if, and using sum if and only if. Okay, it doesn't work. So this should be really simple as well, giving it a sum if and only if. So basically we want a lemma that says that this holds, that if this holds, then this holds and the other way around. So that must be somewhere in the library, yeah? So this is that lemma that I was talking about. Okay, so now seems like, because there's some things in the sim sets basically that destroy the way these lemmas look here. I'll just do the last. Okay, so that's that part. And then the last part, okay, so this is the final refinement. So this basically is equivalent to saying that so F sort is like supposedly a very efficient implementation of what we wanted, and this is a theorem that says that this very efficient implementation is does what it's supposed to do, and the way the way we showed that is by basically refinement. So we show that is frecklist. So we show is list of frequency. Okay, the first one, the most abstract one, and then we show, and then we do one refinement statement step by frequency 1 here. So this is executable, and but with linear complexity, and then again is freq list, but here frequency 1, and then the last step is using red black trees, and the same is frequency list frequency 2. So that's what we're doing, and that's basically the way you do refinement. You have a theorem proving on the most abstract thing, and then you show that the concrete one is equivalent to the abstract one, and then you keep moving this theorem down like that. Okay, so now we want to extract code that is equivalent to what we to the function we proved correct, the most efficient one of them. Okay, so this one must take a string. Okay, and then string here, because strings there is a linear ordering for them based on the topological, based on the lexicographic sorting of characters, and we showed that characters are ordered as well. Yeah. So this is just, we restrict the type here to strings. Remember when we tried to execute that, the definition somewhere here when we had the counter example, it didn't execute because lists in general don't have an order, are not ordered, but strings are ordered. So let's see actually where is that stated quickly. Yeah, so strings are a linear order. Okay, and then this way we can get it to be executable. What I just, so let me try the same example I worked on earlier. Okay, so here for instance, that should be, and then we're going to get the list out of that. Let's just see. F sort string. Okay, and then we have to say that these are all strings, not just lists of characters. Yeah. Okay. So here we have the right map, the right frequency list, and then we can just simply export it to SML that way. F sort string in SML, module name should be that. Okay, so export SML. So now it's working on exporting, and now we have an SML code equivalent to this function, and that code is based on the simplification rules for it. It's just the simplification rules for it form code equations for it. Okay, and then we can load that SML file here in Isabelle in the JEdit interface. Okay, so here you can see, for instance, like implementations of all the data types, and then the different functions. So what's the function that we want? It's called f source string. So let me just look for that. Yeah. Okay, so this function, so you can run this function, like the SML function, by just importing that file and then running this function, f-sort string. It has the same name, but here it expects that input here x, and that x is a list of strings, and it returns to you that. So let's, I will let me just run that SML function here. F-sort string. Okay, we need to import that module first. So here I will actually, but I'll not implement that function here. I'll just show you the function. So this is a wrapper. I will not implement the wrapper here. I will just get this. This is basically a standard thing, a standard piece of code that you get to firstly open a file and transform it into a string. Okay, and then that's more interesting than just running the function on a small string that we're writing manually. And then what we do here, we'll upload all of that in the repository. Those are basically two files I have on my machine that contain so this is file 1 and this is file 2. Okay, so those are two files, and then I will just show you how to use the function that we found in the exported file there, that was exported in the export file there. So this function can be used to sort. So so for example, val it equals, let me just try that, what is it called, f-sort string. Okay, but we need to import the module. So that should be at. So this is this should be an SML function. Okay, so this is the SML function equivalent to f-sort string. Okay, and then we can use this as if it's a normal SML function. So for example, all of this is just standard ML. You can just I would just copy and paste basically that from somewhere I have it. So basically what I'm going to copy now is just a simple function that takes a string like that and tokenizes it. Sorry, a string like what's the content of these files. So let me just show you the content of the file actually, just so you. So 1 second. So I'll open it now to view. So let's say this is, for example, which one? So this is like just a standard focus from you can download it online. So here, like non-fiction, for example, where the non-fiction. So written. Non-fiction, and then copy to. the text. So this is just some corpus of text, okay? And what in order for us to use this function, we have to so this is the function. This is the SML equivalent to the function that I like. This is the SML equivalent to this. Okay, you can just say code at that, and then so of course it won't be file to string, but this file to string of f1. Okay, that of course won't work because this is just a string, but you need a list. What that function expect is a tokenized string. Okay, so we'll just get the standard function, SML functions to tokenize strings, copy them from somewhere. So basically here, this is again, I just corrected the file name because I had the path incorrect. And then what we have here is the following. Okay, so this is a string, and then we just map it to lower case characters because, well, let's remove that. Okay. So basically we want to just tokenize. That's the most important part. Okay. Yeah, but we need to make sure that it is only alphanumeric characters that are in the strings, because the type of let me just, like this string only works for alphanumeric characters and digits, but not other symbols. Okay, so here for example we have the occurrence of the 283 times, of is whatever, etc. Okay, so that's how you run it, and then you can also, instead of doing what I'm doing here, you can just import this like the exported function in an external SML file, and then just do the same wrapper basically. So this is a wrapper to the exported algorithm that was verified. So you can do I'm doing it here from inside Isabelle, but you can also do it from an external file, and here I also did it in an external file, but I won't. So that's it. So basically you do the same, you transform that, and then you tokenize, and then for example you run it on one of those, you run it in a file. So that's it for today, and then the next part will be about the Be Creative projects presentation. So I've put some of them on in the tutorial. There are 3 presentations that I've received, and I have I'm glad I received them. So the first one is by Jakob Schulz, and it's about sparse matrices. And the second one is about by Umar Ahmad, and it's a special version of the Collatz conjecture, formalizing some aspects of it. And the third one is by Niels Mindler, and it's about weak heaps. So he formalized them in Isabelle. So I hope you enjoy those 3 presentations as well. Thank you. So actually one last thing before I close that, I haven't received as many presentations from you as I would have hoped for. So what we're going to hold Professor Nipkow and I, we're going to hold another meeting in the same time of the tutorial, but on Friday, instead of the tutorial, but on Friday, which is going to be after the exam. So the only purpose of that is for you to discuss, like if anyone wants to present their mini project, they can do it on that day, and you can also discuss it with each other. And also you can tell us about whatever you want about the course. So thanks, and I hope you have enjoyed the course, and you can do a lot more with Isabelle. It's more than just this course. So if you enjoyed it and you want to do more projects, you can contact me for bachelor thesis, master thesis, or practicum projects or IDPs. And not only me, like anyone in our chair, in the chair for logic and verification. So Professor Nipkow, me, anyone else, and you can go to the website and see available projects. Thank you very much. I hope you've enjoyed it. Good luck with the exam.